Cosmic abysses, gravity's ultimate triumph. Black holes stand as some of the most captivating objects in the cosmos. These enigmatic entities exert a gravitational pull so intense that nothing, not even light, can escape their grasp. Imagine a place where the fabric of space-time itself is warped beyond recognition, a cosmic abyss from which there is no return. This is the captivating realm of black holes. Black holes form when massive stars collapse at the end of their life cycle. The star's core implodes under its own gravity, compressing matter into an infinitely small point known as a singularity. Surrounding this singularity is an invisible boundary called the event horizon. The event horizon marks the point of no return for anything that ventures too close. Once an object crosses this boundary, it is destined to spiral into the singularity. The immense gravity of the black hole stretches and distorts the fabric of space-time in its vicinity. Black holes challenge our understanding of physics and offer a glimpse into the most extreme environments in the universe. Their study has profound implications for our understanding of gravity, the nature of space-time, and the ultimate fate of the universe.
The event horizon is not a physical boundary, but rather a region of space-time, where gravity becomes inescapable. As an object approaches the event horizon, strange and counterintuitive phenomena occur. Time itself slows down relative to observers at a safe distance from the black hole. Imagine a spaceship approaching a black hole while sending out regular light signals. From the perspective of a distant observer, these signals would appear to take longer and longer to arrive. The light itself is being stretched and redshifted by the intense gravity. As the spaceship nears the event horizon, the light signals would become increasingly redshifted and faint. Eventually, the signals would cease altogether as the spaceship crosses the event horizon. From the observer's viewpoint, the spaceship would appear to freeze in time at the edge of the black hole. For the spaceship and its occupants, however, time would continue to flow normally. They would cross the event horizon unaware of the strange fate that awaits them. What lies beyond the event horizon remains one of the greatest mysteries of modern astrophysics.
As an object falls closer to a black hole, the gravitational pull on different parts of the object becomes increasingly uneven. This difference in gravitational force, known as tidal force, leads to a rather unsettling phenomenon called spaghettification. Imagine a hypothetical astronaut unfortunate enough to fall into a black hole feet first. The gravitational pull on the astronaut's feet would be significantly stronger than the pull on their head. This difference in force would stretch the astronaut's body like spaghetti. As the astronaut falls further into the black hole, the tidal forces would continue to increase. The astronaut's body would be stretched and compressed along the direction of fall, eventually becoming a long, thin stream of matter. Spaghettification is a consequence of the extreme gravitational gradients near a black hole. It highlights the bizarre and often violent nature of these cosmic objects. The process of spaghettification would be incredibly quick, lasting only a fraction of a second for a typical stellar mass black hole. At the very center of a black hole lies the singularity, a point of infinite density and zero volume. Here, all known laws of physics break down, and our current understanding of the universe falters. The singularity represents the ultimate limit of our knowledge. General relativity, Einstein's theory of gravity, predicts the existence of singularities within black holes. However, it also predicts its own demise at the singularity. This is because general relativity does not account for the quantum effects that become significant at such extreme scales. Quantum mechanics, the other pillar of modern physics, describes the behavior of matter and energy at the atomic and subatomic levels. However, attempts to combine quantum mechanics with general relativity to create a unified theory of quantum gravity have so far been met with significant challenges. The singularity at the heart of a black hole represents a profound paradox. It is a place where our current understanding of physics collapses, and we are left to grapple with the unknown. Resolving the singularity problem is one of the major unsolved problems in theoretical physics.